Okay, so previously when we did circular motion, we looked at a conical pendulum. Okay, remember it traces out a cone, right? And I compared that to something that we would eventually see in the future, which is now, okay, the simple pendulum. All right, and I showed you the difference between them is the conical pendulum is more of a 3D perspective, okay, because this thing is going around and it traces out a cone, all right? Whereas the simple pendulum just oscillates, you could just call that in the XY plane. Okay, whereas the conical pendulum is definitely 3D, right? And I asked, which of those looks more complicated? Okay, so to me, the conical pendulum looks more complicated because it's tracing out a 3D cone, all right? But when we found the period, okay, and we found the period of the conical pendulum in the circular motion chapter, all we needed was algebra and trig, and we used Newton's second law, okay? To find the period for the simple pendulum, okay, you need algebra, trig, calc 1, 2, 3, linear algebra, differential equations, and then you would need to change your major to math. And maybe you would look at that your senior year or after that in graduate school. Because it looks at something called elliptic integrals, okay, which you definitely wouldn't get unless you were majoring in math, all right? So obviously, we can't cover all of that today. So we're going to see how we'll get around that. Okay, so a simple pendulum, okay, definition of simple pendulum is a point mass on a string. Okay, so, or a bob on a string. So point mass means that mass is small compared to the length of the string. Okay, so you can't put your shoe there, okay, and oscillate it back and forth because that shoe is large. All right, so a simple pendulum is just a dot at the end of a long string. All right, so if you pull this back, okay, to some initial angle theta 0 and you release it, we want to find the period. Okay, well, first of all, is the motion periodic? Okay, is it harmonic? Well, as you can see in the video, this thing oscillates back and forth. And as long as there's no friction up here at the pivot point, that thing will definitely repeat itself in regular time intervals. Okay, so the motion is definitely periodic. Okay, now, is the motion simple harmonic motion? Okay, so remember there's a criteria for that in terms of what the function has to look like, all right? In other words, it has to go back and forth where the position theta, okay, has to be some function of sine and cosine. Okay, so we want to find the period, all right? So let's look at some parameters that the period could depend on. Okay, I have a mass on the end of a string. So could the period depend on the angle? Okay, that's the amplitude, all right? So you pull this thing back and it'll oscillate back and forth between plus and minus, okay, that theta. Okay, so that would be your amplitude, all right? Does it depend on the amplitude? Okay, because remember, a simple harmonic oscillator does not depend on the amplitude. Remember, you pull the spring back, okay, you keep pulling it back, and we show that this mass on a spring will oscillate with the same period, okay? It might be moving faster with a big amplitude, okay, faster velocity, but the period's the same. So the amplitude is a parameter. Maybe it depends on the length of the string. Maybe it depends on the mass of the bob, okay, that's at the end of the string. So let's find the period and see which of these parameters it depends on. Okay, so what I did is I drew the force diagram. Okay, so here's my pivot point up here. My pivot point on here. Here's my little bob, and I just drew the forces on the bob. Okay, so I have the tension. Okay, I didn't want to use capital T for tension because I'm using capital T for period, and I have the weight of the bob. Okay, so essentially I'm going back to the 5-step method. My picture, forces, okay, coordinate systems based on the direction of the acceleration. Okay, so let's see. So it's moving, well, the bob is moving in a circle, so you have an acceleration toward the center. Okay, you have a centripetal or radial acceleration, all right? But it's also speeding up and slowing down. So this is a non-uniform circular motion, okay? When it's moving upward along the circle, it's slowing down. When it's on its way back down, it's speeding up, okay? Okay, so in this picture, all right, can we tell whether I drew this moving upward or moving downward? Okay, and we're going to see it doesn't matter. All right, so if this thing is moving upward, okay, let's say if that was the direction of the velocity, all right, it's slowing down, okay, right? It's coming to rest as it gets higher and higher, right? So it has kinetic and some potential, and by the time it gets all the way up here at the top, right, that's all potential in the kinetic 0. So we know it's slowing down, okay? So if I have this thing moving up, right, and it's slowing down, then you know the acceleration has to point backwards, has a tangential acceleration that points in that direction downward. Okay. Now, what if it was moving in the other direction? Okay. Let's say in this picture it was headed, it had already gone up, and it was headed downward. Okay. Well, it was headed downward, it's now speeding up. So the acceleration would point in the direction of the velocity. Okay. So in this picture, it doesn't matter whether I drew this thing rising or falling. Okay. The tangential acceleration is in the exact same direction. So that dictated my coordinate system. Okay. I had an acceleration toward the center. Okay. I have a tangential acceleration in that direction. So essentially this is like my X and Y axis. All right. Okay. And then what forces did I break up? Well, I have to break up mg because tension points along the string. So I have to break up mg. So that's my angle. That's my angle theta. So that one's theta. This one's adjacent. That's my mg cosine. There's my mg sine. Okay. All right. So I'm going to write down Newton's second law in, I called it the y direction. Okay. So it's the tangential direction. All right. So I need to look at the tangential force. So the tangential force is mg sine. Okay. So the tangential force is mg sine. Okay. But I have to add the minus sign. Okay. Why do we need the minus sign? All right. Well, if I don't include the minus sign, okay, if I ignore the minus sign, that says that even when this thing passes over here, okay, it passes over the equilibrium position. Okay. Once it passes over here, if I didn't have the minus sign, that would say that mg sine still points in that direction, and this thing would just keep looping around. Okay. And that makes no sense. Okay. So the minus sign is there. Remember, the minus sign is there to indicate that mg sine is a restoring force. Okay. So that means that mg sine is always in a direction, okay, that's opposite the displacement from the relaxed position. Right? So I drew a little arrow down here because this picture up here, the pendulum, okay, the treatment of that reminds you of the mass in a spring. So here's our pendulum I drew over here. Okay, that's the one over there. So mg sine theta is pointing in that direction. Well, if I project it down, if I look at a mass in a spring, okay, when the mass is over here, spring force points inward toward the equilibrium position, okay, toward the relaxed position. When the pendulum swings over here, okay, when it's at that point, my mg sine has now switched direction. It now points downward to the left, but it's always in the direction toward the equilibrium position. In other words, this is where the mass would hang if you just put it on a string and didn't touch it, right, at the middle point. Just like this is where the mass and spring would like to stay, right? That's the relaxed position, okay? So this whole business of a restoring force reminds you exactly of when we did the spring force, minus kx, right? The minus sign is there, okay, to show that the spring force is a restoring force. It changes direction, okay, when the spring crosses over the equilibrium position. Okay, so that's what the minus sign's there for. So I go down here. Okay, so I'm applying F equal ma in the tangential direction. So my tangential force is my mg sine. Okay, there's my mg sine with the minus sign. That's equal to ma tangential. Okay, but for something moving in a circle, when we did the rotational chapter, okay, a tangential is r alpha. Okay, what plays the role of the radius? Well, that's the length of the string. So right here where I have a tangential, I'm going to put in r alpha, where the radius r is the length of the string. Okay, let me get rid of the m's. Okay, and I solved this for alpha, just divide by L. So I solved this for alpha. Okay, that's the angular acceleration. Okay, so I just rewrote that right there. Okay, so again, I'm trying to find the period. Okay, we're trying to find where is a capital T going to come out of here. Okay, so remember alpha, angular acceleration, is the second derivative of the angular position. Okay, so where I had alpha, I put in the second derivative of theta with respect to time. All right. Okay. So I look at this, and I want to remember what we did for the mass and spring simple harmonic motion. Okay, so we have the second derivative here, okay, which looks familiar. Okay, you got a theta here, you got a theta over there, and I have this thing. I have G over L. So I want to look at what are the units of G over L. Okay. Well, G is gravity, meters per second squared, and L is the length of the string, that's meters. Okay. So the M's cancel out, and I'm left with 1 over seconds squared. So then what I can do is inside, I can write the word radian for free, all right, because the radian's a dimensionless quantity. And then I look at that and I say, ooh, that's the same units as omega squared. Okay, so then G over L, that G over L has the same units as omega squared. So what we're going to do is we're going to call this thing omega squared. Okay, so then we want to ask, does this right here, does this expression, okay, does this have the form for simple harmonic motion? Okay, so what if the final exam was one question, yes or no, right? And people kind of go like that. Okay, that's not good. Okay, so is this the form for simple harmonic motion? Okay, well, to answer that, we got to go back. Okay, I got to look at the math part of it. So we did the math on a spring. Okay, that was our equation of motion for simple harmonic motion. Okay, meaning this was the equation that gave you the sine and cosine solutions. Okay, so remember the pattern. Here you have the function x. You take two derivatives minus a constant. You get minus a constant times the same function back. Okay, so you have a function. You take two derivatives. You get minus a constant times the same function back. This is what we have here. Well, our function is theta. Okay, here you take two derivatives. That's good. You get minus a constant. That's good. But you don't get theta back. Okay, you get the sine of theta. Okay, so that does not fit that form. Okay, a function, two derivatives, minus a constant times the same function back. Here you don't get the same function back. You get the sine of the function back. Okay, so that's not simple harmonic motion. So actually, for this pendulum, okay, all right, if you look on Wikipedia for simple pendulums, okay, the period actually has this form. Okay, depends on the length of the string. Okay, depends on what planet you're on, all right? But it depends on the amplitude. Okay, so theta initial is your initial amplitude, meaning how far you initially pull it back. Okay, so this says that if I pull it back a certain angle, okay, and again, these angles would have to be in radians. If I pull it back a certain angle, okay, and I let it go, I can calculate the period. Okay, but if I double the angle, okay, if I change theta, that says the period changes. Okay, so the period is not independent of the amplitude. Okay, so this is not simple harmonic motion. Okay, but we want to look at simple harmonic oscillators. Okay, because we know how to deal with them. So what we're going to do, okay, is we're going to force the motion to be simple harmonic motion. Okay, and how we do that, you're going to see this a lot, especially in the 196 E&M course. Okay, is you're going to use something called the small angle approximation. Okay, so go back to Calc 2 for a little bit. Okay, so you remember the Maclaurin series, or you could also call it the Taylor series for sine. Okay, remember sine is an odd function. Okay, it's an odd function, so that's why you get all odd powers of theta. Okay, hopefully that's how they told you to memorize that. Okay, so 1, 3, 5, and 7. Okay, so remember when you write this series, okay, all right. This doesn't say that the sine of 10 degrees is 10 and then 10 cubed, right? No. Okay. So remember, theta has to be in radians. Okay. So what the small angle approximation is, okay, is for small angles. Now, what is a small angle? All right. So we say theta is less than or much less than 1 radian. Okay. Now, what's a radian? Okay. So that's 0 radians. That's pi over 2. Remember, pi over 2 is about 1.57 on a calculator. Okay, so 45 degrees is about 0.78 radians. Okay, so much less than 1 radian, right? So that's 1.57. Okay, that's 0.78. So let's say you're much less than 1 radian. Maybe you're down here, I don't know, like 20 some degrees. Okay, as long as you're less than a radian. Okay, much less than a radian. So maybe 22.5 degrees would be about 0.4, okay, radians. Okay, so in other words, you pull the pendulum back, that'd be 22.5 degrees, so about 0.4 radians. So the idea is with the Taylor series, okay, with these powers of theta, okay, when you take a number less than 1, Okay, that number is less than 1. That small angle in radians is less than 1. When you take a number less than 1 and you cube it and raise it to the 5th and raise it to the 7th, okay, numbers that are less than 1, they get smaller. Okay, so for a small angle, when you put a small number in for that theta and you raise it to those powers, okay, these terms get small. Okay, what do you mean by small? They're small compared to the one you're going to keep. Okay, so when you have a number less than 1 and you cube it, raise it to the 5th, and raise it to the 7th, especially when you're dividing it by the 3, 5, and 7 factorial, these numbers get small compared to that one. Okay, now, remember from Calc 2, all right? Here's the Taylor series, you can call it the Maclaurin series. Here's the Taylor series for sine x. Okay, remember, there's a 1 right there, right? It's all odd powers of x, all right? So the whole idea of this is looking up at the graph. If from algebra class, if you graph y equals x, okay, that's a straight line. That's the red line. Okay, y equals x, all right? Well, the whole idea of the Taylor series is, so this function approximates y equals sine x, and you get a better approximation the more terms you keep. So if you look at the picture up here, all right, so if I look at, where's the blue one? Okay, the blue one is the 9. So if I look at the blue curve, okay, there's my 9 right there. Okay, if I look at the blue curve, if I keep the terms all the way up through the 9th power, okay, so in other words, you put all that in your calculator, okay, or in a computer, and you graph that, okay, it's going to look like the blue line, okay. So, and this line here, the black line, okay, that's y equals sine x, okay. So the blue line, which is the first 1, 2, 3, 4, the first 5 terms for the Taylor series for sine, that blue line, okay, which is a polynomial, approximates y equals sine x for large values of x. So if I look at the blue and black line, okay, so they're right on top of each other. So if you look right around here, okay, they're on top of each other, okay, and then they start to deviate right about there is where they come apart, okay. Now if you kept, okay, up to the 11th and the 13th, okay, so the 6th term and the 7th term, where it's x to the 11th and x to the 13th, okay, then they show the 11th one. They also show the 13th as that one, meaning it approximates the sine for even larger values of x. Okay, the further you go out, it still looks like the sine. Okay, if I look at the 3, okay, that color one, okay, so if you keep the first 2 terms, okay, that's this one here. So that approximates this y equals sine x for bigger values of x, right? It starts to break up right around there, okay? But the important one we want to look at, okay, is the first term, okay? So if I just kept that first term, okay, y equals x, that's the red line, all right? And I look at, well, for how many values of x, how big can x be, where that red line lays on top of the black line y equals sine x. So if I blow that up here, okay, they're almost right on top of each other, right through here, okay. Well, what values are that? Okay, well, you see it deviates right here, so it breaks apart there, okay, and the top of the sine, okay, right there, that's pi over 2, okay, and pi over 2 is about 1.57, okay, so remember we said theta had to be much less than 1, that's not less than 1, it's 1.57. So you go a little bit inward, maybe halfway in between, okay, that's pi over 4, okay, pi over 4 was our 0.7 something, okay, so you're less than 1, and it just starts to kind of deviate from there, all right, so even at 45 degrees, okay, right there, even at 45 degrees, that's not a bad approximation. And then when you get closer, okay, when you're here at about 22 degrees, okay, right there about 22 degrees, okay, then those two lines are right on top of each other. So sine x, okay, sine x is approximately equal to the first term x, okay, for those values of x from just on the right side, from 0, maybe up until about there. They almost coincide, those two lines, Okay, so that's the small angle approximation. So let's go back here. Okay, so as long as the angles are small, okay, much less than, we said, much less than 22 degrees, okay, then sine theta is approximately equal to theta, okay. Now, as an aside, okay, the other small angle approximation you'll see, especially next semester, is not only is sine theta approximately equal to theta, okay, but it's also approximately equal to tangent theta, because tangent is sine over cosine. So here's the first couple terms for sine. There's the first couple terms for cosine, okay. When theta is much, much less than 1, okay, that term gets small, that term gets small because you're raising it to a power. That term gets small, that term gets small, and all you're left with is theta over 1, okay, which gives you theta. So the small angle approximation you'll often see is sine theta is approximately equal to tan theta, which is approximately equal to theta, okay. Now again, okay, gotta be careful, all right. This doesn't say, here, where can we put it, that sine of 5 degrees is approximately equal to 5. No. Okay, remember, theta has to be in radians, okay? So to test this whole small angle business, okay, if I look at theta as 5 degrees, okay, 5 degrees is somewhere over there, okay? So those two lines at about 5 degrees, okay, if I convert 5 degrees to radians, it's probably around here somewhere. They're right on top of each other, okay? But mathematically, what that means is you take 5 degrees, okay, on your calculator, convert it to radians, right? So remember, you have to do 180 degrees is pi radians, multiply it by pi over 180. Okay, do that. Okay, so if I convert that to radians, I get that many radians. Okay, so this number is now sitting on your calculator. Okay, make sure your calculator is in radian mode, and then you press the sine button. So when you take the sine of that number, okay, and look at your screen, it goes from 8727 to 8716. It only changes by about 11, right? 16 to 27 is 11. It changes by about 11 out of 8,700. Okay, so to say sine theta is approximately equal to theta for about 5 degrees, that's good to within 0.1%. Okay, now I go to a bigger angle. Okay, so I pull my pendulum back to 20 degrees. Okay, remember, where was 20 degrees? Okay, that was 45. That's 22.5, so 20 degrees should be pretty good. Okay, so if I convert 20 degrees to radians, okay, remember, multiply by pi over 180, convert it to radians, hit the sine button on your calculator, the number is going to change on your screen from 3491 to 3420. So it's going to be different by about 70 out of 3400. So to say sine theta is approximately equal to theta for theta equals 20 degrees, okay, that's good within about 2%, okay? Now, when you get up to 45 degrees, okay, 45 degrees we said was here. So you can see that's when the red line y equal x starts to deviate from the black line y equals sine x at that 45 degree mark, okay? So we do it at 45 degrees, okay? I convert 45 degrees to radians, okay? Hit the sine button, and now the number on your screen goes from about 7,800 to about 7,000. Okay, I'm ignoring the decimal. So that changes by about 800 out of about 7,000. So now that's a large change. Okay, so to say sine theta is approximately equal to theta for 45 degrees, that's only good within about 11%. So for small oscillations, okay, meaning we're going to take our pendulum, maybe pull it back to less than 20 degrees, okay? So for small oscillations, and sine theta is approximately equal to theta, then we can write sine theta here as theta, okay? So this is a small angle approximation. We're forcing our simple pendulum to be a simple harmonic oscillator by only oscillating it at small angles. Okay, so this is the form, okay, that is the form for simple harmonic motion. Here's my function, theta, take two derivatives, get minus a constant, times the same function back, okay? So the solution, okay, the solution to an equation like that, all right, is theta max cosine or sine of omega t plus phi, okay? Now, we have to go way back, okay? We had this business here, okay? So omega, where'd it go? So omega squared, was G over L. We called this thing omega squared. Why was that? Because it has the same units as omega squared. So omega squared is G over L. Okay, so down here, okay, if we have this written, okay, that box says that this is the solution, okay, but you have to remember omega squared was G over L, so omega is the square root of G over L. Okay, so for small angles, then the simple pendulum is a simple harmonic oscillator. Okay, so omega squared of G over L, all right, and then what I did is to find the period, okay, period is 2 pi over omega, okay, so that's square root of G over L, so period is 2 pi over omega, okay, so the L flips up on top, and that gives me the period for my simple pendulum. Remember, anything you know about the period, you can easily deal with the frequency, because the frequency is 1 over the period, okay, so if you have the period, you instantly now have the frequency, okay, so since we forced the motion to be simple harmonic by using a small angle, okay, all right, in doing that, we found that we forced the frequency and period to be independent of the amplitude, okay. Way back here, where to go? Way back here, okay, it turns out that if you pull this thing back, I don't care, like at 55 degrees, okay, and let it go, the period is not independent of the amplitude. Okay, it's a solution of an elliptic integral. It's a big mess, okay? But the advantage of forcing it to be a simple harmonic oscillator is if you pull this thing back to 5 degrees and let it go, there's the period, okay? If you double the amplitude maybe to 10 degrees and pull it back, period really doesn't change, okay? So some of the parameters, okay, what does the period depend on, okay? It just depends on the length of the string and what planet you're on, okay? So if they stood there on the moon and they had a little pendulum going back and forth, they know the length of the string, you could measure the period, and you could measure G for the moon, okay? We're gonna do, I'll show you a video, okay? And this is the easiest way all semester to measure little g, okay? We couldn't do it in chapter 2 because they had to sit through 15 chapters almost of physics to get to the simple pendulum, okay? But if I take the period, so I'm going to square both sides and then solve that for G, okay? So G would be 4 pi squared L over T squared, okay? So I'm going to show you a simple pendulum, okay? I think the length is about 44 centimeters, okay? And you're going to measure the period, and then we can calculate little g. It's that simple, all right? Now, obviously, if someone lets this thing go and it goes one cycle, okay, that wouldn't be very precise to measure the period. So we're going to measure 10 periods, okay? So you let this thing go, okay? So actually, it can be let go, all right? You let go of it, and it can start swinging, and then you walk over and get your timer, okay? And then you can go click, 1, 2, 3, and so on. All right, so I'm going to show you a video. There's a little pendulum, okay, or a little pendulum bob, okay? L is the length of the string, so it's about 44 centimeters. And it's released here from rest, and this thing's going to swing back and forth, okay? Now again, it wouldn't be very precise to just measure one cycle, okay? You're going to measure 10, all right? So you're going to measure 1, 2, 3, 4, and so on, okay? So, and it doesn't matter when you start. This thing can be going back and forth, okay? And you can decide to start right there. Click. 1, 2, 3, 4, and so on, okay? So you're going to measure 10 periods or 10 cycles, all right? So I'm going to play the video, okay? You can rewind it a couple times trying to figure out what's a good place to start. So what I do is the person releases it, okay? And I wait maybe 1 or 2 swings, okay? Maybe they release it, and then I'm going to start click, 1. Whoops, I messed it up. See that? They release and it goes click, 1, 2, 3. So it doesn't matter when you start, as long as wherever you start, that's where you count. Or you want to start when it's at the bottom. They release it here. You can go, they release, click, 1, 2, 3, 4. So Sometimes it's easier to pick an endpoint. They release it here, let it go, click. 1, 2, 3. Okay, so watch the video, and I want you to count 10 cycles. Okay, so when I count at 10 cycles, I got about 13.3 seconds. Okay, so the period, capital T, is that total time divided by 10. So that gives me the period. All right, so I'm using this expression. Okay, I know the length of the string is about 44 centimeters. Okay, I use my stopwatch to get the period. Right, and I get 9.82. Okay, so the two sig figs, I get 9.8. So if I compare the 9.82 to the 9.8 or 9.80 in the book, I get less than 0.2, or I get about 0.2%. Okay, and then you get to put a smiley face on that. Okay, so just using a piece of string, maybe your shoelace, and something small, okay, not too light, you don't want a paper clip because there's too much air resistance, but something small and heavy enough, you can calculate that little g probably wherever you're sitting right now to within like 1%.